4.6 billion years ago, there were no oceans, no mountains, and no planets. Instead, there was only a vast, cold cloud of gas and dust drifting through a dark universe. Over time, the subtle pull of gravity took hold of this giant molecular cloud, forcing the scattered matter to collapse in on itself. As the cloud condensed, it began to spin faster and faster. Deep in the center, the pressure built until it ignited a newborn star, our Sun. The remaining peripheral material didn't fall into the star. Instead, the intense rotation flattened it out into a massive, swirling disk of debris orbiting the young Sun. This spinning disk of primordial gas and dust became a chaotic nursery, planting the physical seeds that would eventually grow into our entire planetary system. Inside that swirling disk, the environment was incredibly crowded. Glowing particles and loose rocks whipped around the Sun at immense speeds. Through a process called accretion, these tiny rocks repeatedly crashed into each other. The intense heat and gravity allowed them to fuse together upon impact, slowly building larger planetary bodies. Planetary formation resembled a brutal demolition derby, driven by millions of high-velocity collisions. As a direct result of these immense impacts, the newborn Earth was entirely uninhabitable. The sheer kinetic energy left the young planet as a fiery, roiling ocean of molten magma. A relentless rain of meteorites continued to bombard the surface from above, keeping the molten rock churning and severely overheated. Earth was forged in extreme chaos, barely a stable world at all, struggling against gravity and constant impacts to hold its mass together. If you look beneath that violent surface into the completely liquid interior, a massive physical problem emerges. A chaotic ball of liquid magma somehow had to develop structural integrity.
In this cross-section of the early molten Earth, we see planetary differentiation. Gravity acted on the fluid body, pulling heavy metals like iron and nickel downward to form a solid core. This displaced lighter silicate rocks, which floated upward to the surface. This massive internal sorting process established Earth's permanent anatomy. It created a dense metal core, a thick rocky mantle, and a solid outer crust, bringing the very first semblance of order to a chaotic world. Down at the center of the Earth, that newly formed metal core was incredibly dynamic, churning as a rotating sphere of liquid iron. This core model shows the dynamo effect. The liquid metal's rotation generates a powerful electromagnetic field extending into space. This invisible shield catches and deflects deadly cosmic radiation and solar winds away from the surface. If that internal sorting hadn't occurred, Earth would lack this magnetic shield. It would have remained a barren, irradiated rock, its atmosphere stripped away by the sun, entirely incapable of supporting life. With its internal structure organized, the environment on the surface finally began to shift. The outermost layer of magma slowly cooled, hardening into a primitive, solid crust. Rising steam and heavily trapped volcanic gases vented from the deep interior, gathering above the crust to form a thick, protective early atmosphere. The skies began to clear. The relentless, fiery bombardment from surrounding space debris that had characterized the planet's birth slowly faded away. The initial chaos had subsided into a fragile stability. For the very first time in its history, Earth looked like a structured, surviving planet. But out in the deep, dark void of the solar system, well past Earth's newly stable orbit, a massive threat was lurking. From the darkness emerged a giant Mars-sized rogue world. This massive object, often called Theia, was caught in Earth's gravitational pull. It was accelerating along a direct, unavoidable collision course with our planet. An impact of this magnitude guaranteed total devastation. The sheer force would be enough to vaporize the entire crust and completely tear the newly structured world apart. Yet this specific cycle of extreme destruction would eventually leave behind a permanent companion in the night sky, our moon. But at this moment, just as Earth achieved a brief window of order, its most violent physical transformation was only seconds away.
When we look up at the night sky, the moon seems like a permanent, peaceful fixture of our world. It orbits in a quiet rhythm, pulling the tides and softly illuminating the dark. But how did this perfect celestial partnership actually begin? To find the answer, we have to rewind 4.5 billion years. Back then, our home was completely unrecognizable. A single day lasted only about 4 to 6 hours. The surface was a boiling ocean of magma, churned by massive volcanic eruptions and asteroid impacts. There was no solid ground, no liquid water, and absolutely no chance for biology to take hold. Drifting through this volatile early solar system was another young world, a wandering Mars-sized protoplanet named Theia. Caught in the gravitational pull of the sun, Theia was locked onto a trajectory that intersected directly with our own. The two worlds were hurtling toward a devastating impact. Yet the total destruction of this early Earth was the exact sequence of events required to build the habitable planet we live on today. When Theia and Earth finally collided, they released energy equivalent to billions of nuclear bombs detonating all at once. The sheer kinetic force of the crash completely shattered Theia. Its heavy metallic core sank and merged with Earth's, while the intense heat instantly liquefied whatever fragile crust had begun to form on our planet. The explosion blasted billions of tons of superheated, vaporized rock out of the atmosphere and straight into the freezing vacuum of space. This animated diagram shows how Earth's gravity captured that ejected mass. Instead of drifting away into the solar system, the crushed remains of Theia and Earth's upper crust were stretched out, forming a dense, glowing ring of magma and dust around the surviving planet. Our planet barely survived the encounter, but this massive ring of suspended rubble provided the exact raw materials needed to build a second celestial body in our sky. The chaos of the initial blast eventually faded. In its place, the relentless force of gravity began to organize the debris field over thousands of years. We can see the mechanics of accretion here. As rock particles bump into each other, they stick together, fusing into heavier clumps. As these grow, their gravitational pull strengthens. The largest fragments act like cosmic vacuums, absorbing all the smaller debris in their path. Eventually, these massive chunks of rock accumulated enough matter to collapse under their own weight, rounding out into a single cohesive sphere. From the ashes of a global catastrophe, the Moon was complete. It began its permanent orbit around a heavily scarred, rapidly cooling Earth. The very forces that tore the planet apart had forged a companion, tying the two worlds together in a shared gravitational system. Over the next few billion years, the Moon slowly drifted further away from the Earth, allowing both worlds to settle into a predictable routine. Here we see the Moon's physical impact. Its gravitational friction acted as a brake, slowing Earth's frantic 4-hour days into a steady 24-hour rotation. This tether also locked our wobbling axis into a permanent tilt and began dragging our oceans, creating nutrient-circulating tides. By holding our spin and our tilt constant, the Moon prevented wild, destructive swings in global temperature. This steady physical environment called the early extreme weather patterns and provided the long-term climate stability required for complex biology to develop. The tranquil blue oceans and predictable seasons we rely on are a direct result of this ancient, invisible partnership. If Theia had missed, our planet would likely still be a hostile, rapidly spinning rock. The greatest disaster in our history provided the silent guardian that built our life support system. In the immediate aftermath of the Moon's formation, Earth was a sphere of boiling rock. Temperatures across the surface reached thousands of degrees. There was no solid ground to stand on, no breathable air, and absolutely no possibility of sustaining biological organisms. Yet this violent ocean of magma occupies the exact same cosmic coordinates as the quiet blue world we inhabit today. To get from that glowing wasteland to a biological sanctuary required a highly specific sequence of events. Nothing about our planet's survival was guaranteed. It relied on a precarious chain reaction unfolding over millions of years, where every single physical transformation had to happen in the correct chronological order. The first necessary shift was a massive drop in temperature. Over millions of years, the intense heat of the early solar system began to dissipate. As the surface cooled, the sprawling oceans of lava began to harden, forming a thick, solid crust of volcanic rock across the entire planet. This new crust acted like a lid. The immense heat trapped below drove continuous volcanic eruptions, venting enormous quantities of steam high into the primitive sky. The bright glow of magma was replaced by a dark, ash-covered sphere, completely shrouded in a thick, suffocating layer of water vapor. Without this cooling phase creating a solid planetary seal, that moisture would have dissipated into space, stopping the chain reaction before it could truly begin. As temperatures continued to fall, the atmosphere hit a critical threshold. The rising steam began to condense into heavy liquid droplets. Then the skies opened. A torrential downpour began that would last for thousands of years without a single break. This relentless rain poured across the newly formed crust, slowly pooling in the massive, rugged impact craters and geological basins. These expanding pools of water eventually merged to form Earth's first oceans, permanently altering the surface chemistry of the planet. Every biological process we know of requires a liquid medium to function. Water provides that exact environment. But holding on to those oceans was another matter entirely. Liquid water is highly vulnerable, and in the harsh environment of a young solar system, it is easily stripped away. The greatest threat to this new water came from above. The young sun was constantly erupting with deadly solar radiation. These high-energy streams of solar wind carry enough force to gradually tear away a planet's atmosphere, taking every drop of surface water with it. To protect its oceans, Earth relied on an engine buried thousands of miles underground. Deep within the planet, a molten, spinning iron core acts as a massive geological dynamo, generating a powerful electromagnetic field. This invisible field pushes out far beyond the atmosphere, where it catches and deflects the incoming solar wind away from the vulnerable planet. If that internal dynamo ever stopped spinning, the solar wind would scour the planet dry, ending any chance for biological life to develop. With the planet shielded from above, the focus shifted to the deepest, darkest trenches of those early oceans. Along the fractured seafloor, hydrothermal vents became active zones, where the hot crust released a continuous flow of minerals and thermal energy into the water. It was inside these highly specific, pressurized, chemical-rich environments that a nearly impossible physical reaction took place. Simple, microscopic organisms began to emerge. Over time, these single-celled structures multiplied and spread throughout the global ocean. Every plant, animal, and human that will ever inhabit this planet traces its direct lineage back to those primitive cells. The combination of cooled volcanic rock, heavily protected water, and abundant chemical energy finally completed the necessary recipe, bringing the chain of Genesis to a close. From the distance of space, the millions of years of violent, chaotic evolution settled into a stable, quiet equilibrium. The fiery collisions birthed a solid rock surface. That rock trapped and held on to liquid water, and a spinning iron core protected that water from the sun. Finally, inside those protected oceans, organic chemistry sparked biological life. The odds of these specific events occurring in this exact order are astronomically low, resulting in what is currently the only known biological sanctuary floating in a dead cosmos. But Earth did not maintain this delicate balancing act entirely on its own. Hanging silently in the background, its scarred, dead companion has been secretly stabilizing and shaping our planet's destiny from the very beginning.
This is an ancient, airless terrain. It is a world of stagnant dust and deep shadows, completely devoid of the oceans and atmosphere required to sustain even the simplest forms of life. For billions of years, this silent landscape has remained virtually unchanged, locked in a perpetual orbit as it observes our planet from the vacuum of space. But looking back from this desolation, we see a vibrant, swirling blue sphere. Despite the vast distance between them, the physical relationship between these two worlds is the primary force governing our environment. The early solar system was defined by violent collisions and erratic planetary shifts. While many worlds were left in chaos, Earth secured a unique and enduring stability. This proximity creates a constant, invisible interaction. The Moon functions as a planetary anchor, exerting a physical influence that dictates the behavior of our oceans and the very tilt of our world. Nearly 384,400 kilometers of empty space separate us. Across that expanse, a massive gravitational tether locks our two worlds together. This force functions like a planet-sized magnet, exerting a constant, rhythmic pull on everything resting on the Earth's surface. We see this gravity in action every day as billions of tons of ocean water surge forward and recede against the world's coastlines. Over millions of years, these relentless tidal shifts have aggressively sculpted the land and driven the evolutionary rhythms of every marine ecosystem on the planet. For humans, mapping these lunar-driven patterns was an essential survival tool. The predictable ebb and flow dictated global navigation, guiding maritime explorers across uncharted oceans for centuries. Without this constant gravitational grip churning the seas, our oceans would be stagnant. The global distribution of nutrients would fail, and the biosphere we rely on would be unrecognizable. The moon's influence extends beyond the water. It controls the mechanics of how the entire globe rotates in space. Our planet spins at a steady 23.5 degrees, held in place by the moon acting as a massive external gyroscope. If that anchor disappears, the stabilizing force is lost. Earth's axis immediately drifts, wobbling violently as it orbits the sun. This unchecked wobble would trigger massive, chaotic climate swings. Polar ice could rapidly shift toward the sun, causing sea levels to rise and equatorial regions to freeze in a matter of centuries. By locking our rotation into a predictable rhythm, the moon provided the long-term climatic stability required for complex life to evolve and survive. For eons, this distant gravity forced Earth into a sheltering rhythm. But in the mid-20th century, humanity began to engineer a way to traverse that invisible tether. After millennia of observing our neighbor, we began to build a bridge across the vacuum. Breaking free of Earth's gravity required harnessing immense explosive power. Engineers stacked thousands of tons of volatile propellants into towering metal silos, riding controlled detonations into the void. This wasn't just a feat of physics, but of intellectual coordination. Thousands of flight controllers and mathematicians collaborated to calculate the exact trajectories required to reach the lunar surface. That effort culminated in a single physical action. Human boots finally disturbed the lunar dust, breaking billions of years of absolute silence. These missions immediately prioritized the extraction of pristine lunar material. These samples provided the physical evidence needed to decode the history of the entire solar system. The Apollo missions proved that we could successfully operate on another celestial body, changing our perspective on what was possible for our species. Today, the goal has shifted from brief exploratory visits to a permanent human presence on the lunar surface. The Artemis program is the modern successor to those early missions, utilizing advanced orbital technology and heavy lift propulsion systems. Engineers have designed hardware like the Orion spacecraft specifically to sustain and protect astronauts during the extended durations required for deep space operations. The strategic objective is to build sustainable research foundations directly on the lunar surface, allowing crews to live and work there for months at a time. The physics of the moon offer a significant advantage. Because its gravity is only 1/6 of Earth's, launching a spacecraft from its surface requires a fraction of the fuel, making it an ideal staging ground for the stars. Our closest neighbor has evolved in our understanding. The ancient stone that anchored our past is being forged into the vital physical gateway for humanity's future on Mars and beyond. For most of human history, looking up into the night sky meant looking at a single, dominant feature. The moon was the most prominent and constant world visible to early civilizations. Because of its reliable 29.5-day cycle, it became a fundamental tool. Ancient cultures mapped these phases to track the passing of seasons, coordinate agricultural harvests, and weave complex mythologies around its presence. Over time, humanity's approach to the moon shifted. When astronomers first pointed primitive glass lenses toward the sky, the moon transitioned from a subject of myth into our first object of true scientific observation. But even with these early telescopes, nearly 250,000 miles of empty space stood between the lens and the lunar surface. Observers could map its craters and name its seas, but it remained entirely out of reach.
For 99% of human existence, the moon was an untouchable muse. We could look, but we could not touch.
That historical permanence makes the sudden technological violence of the 20th century all the more striking. The invention of the modern rocket abruptly made Earth's atmosphere permeable. This Soviet launcher represents the shift from ground-bound conflict to orbital capability. Yet the initial drive to leave the planet was not fueled by scientific curiosity. Space exploration began as an ideological demonstration of global supremacy. The United States and the Soviet Union locked into an escalating space race. Reaching the moon required an entirely new industrial scale and raw, sustained force to push massive payloads out of Earth's gravity. In July 1969, Apollo 11 achieved the objective. When astronauts walked on the lunar surface, it effectively ended the geopolitical competition, providing a definitive victory for the United States. This raises an interesting contradiction. If the race was won decades ago and the finish line was crossed, why are global superpowers currently spending tens of billions of dollars to go back today? The answer is that we initially misunderstood what the moon actually had to offer. To justify the immense cost of returning, space agencies had to stop viewing the moon as a trophy and start viewing it as a tool. A moment of wonder. Standing on a barren, airless rock provided humanity with a completely new perspective. Looking back at Earth suspended in the blackness of space replaced Cold War tension with a profound sense of isolation and awe. Human contact with the lunar surface transformed the mission objectives. The focus shifted from the symbolic act of landing to the practical requirements of rigorous field geology. The astronauts functioned as the first extraterrestrial field geologists. They deployed solar wind experiments, set up seismometers, and crucially, gathered hundreds of pounds of rock and soil samples to bring back to Earth. This diagram shows a molecular comparison between a lunar rock sample and Earth's mantle. The identical isotope ratios led scientists to the giant impact hypothesis, the understanding that the moon was formed from the debris of a massive collision with a young Earth. Because the moon has no atmosphere, no weather, and no active tectonic plates, its surface remains virtually unchanged. The craters and rocks sit exactly as they have for billions of years. Ultimately, Apollo proved that the moon is a pristine laboratory. It holds a perfectly preserved geological record of the violent collisions that created our own planet, a history that wind and water have long since erased here on Earth. Today, we see the deployment of the Orion capsule. This hardware is engineered for the long-duration mechanical and physiological demands of deep space exploration. The mission geography is also changing. Apollo targeted the relatively flat, safe regions near the lunar equator. The Artemis program, however, is aiming for the rugged, heavily cratered terrain of the lunar South Pole. Space agencies are targeting the South Pole because of a single critical resource discovered there: water ice. If astronauts can harvest this ice, it can provide drinking water and breathable oxygen, or be split into hydrogen and oxygen to create chemical rocket fuel. Moving the heavier payloads required to harvest these resources demands massive next-generation launch systems. Rockets like the Space Launch System are engineered to push the heavy infrastructure needed for long-term survival into lunar orbit. This means Artemis is not designed for brief exploration. It represents a structural shift, aiming to establish a permanent, sustained human presence on another celestial body. Living on the moon long-term requires surviving an exceptionally hostile environment. Any permanent base must withstand unfiltered solar radiation, constant micrometeorite impacts, and temperature swings of hundreds of degrees. To manage these extremes, conceptual engineering designs suggest moving underground. Habitats will likely need to be partially buried or coated in thick layers of local lunar dirt, known as regolith, to provide adequate radiation shielding. Human astronauts will not spend all their time performing manual labor on the surface. Instead, they will act as field supervisors, overseeing fleets of autonomous robotic rovers and excavators that handle the heavy, dangerous operations outside the habitat. This map outlines the lunar South Pole, highlighting high-elevation ridges known as the peaks of eternal light. Placing solar arrays here ensures constant sun exposure. This continuous power drives machinery inside neighboring, permanently shadowed craters,
where freezing temperatures trap water ice. Through this combination of power generation, resource extraction, and robotics, the Moon is transitioning. It is moving from a purely scientific destination into humanity's first fully operational off-world infrastructure project. But surviving on the Moon is not the final objective. Establishing this lunar infrastructure is actually a necessary staging ground for moving deeper into the solar system. This diagram compares Earth's gravity well to the Moon's. Launching fully fueled spacecraft from Earth requires enormous energy. By converting lunar water into propellant, spacecraft can launch partially empty, stopping in lunar orbit to refuel. The Moon becomes a low-gravity refueling station. Furthermore, testing human survival systems just 3 days away on the Moon serves as a mandatory rehearsal. Engineers need to know their life support and habitation tech works flawlessly before sending a crew on a one-way 7-month transit to Mars. Our activity on the Moon serves as the functional starting line for the solar system. It is the platform from which humanity moves toward Mars and beyond.
Look across the billions of worlds scattered throughout our galaxy, and this is the only location where we can confirm that life exists. While the space surrounding it is a cold, irradiated vacuum, the surface of this rock supports deep liquid oceans, breathable atmospheres, and complex biological networks. This biosphere has been active for more than 4 billion years. In that time, the planet has absorbed the impact of massive asteroids, endured intense periods of global volcanism, and frozen over during deep ice ages. Despite extreme geological trauma, the Earth has maintained a fragile, functioning life support system. That system is driven by powerful natural forces. The Earth's crust constantly tears apart and rebuilds itself, venting heat and ash into the sky. Recently, human industrial activity has introduced a new variable, shifting the chemical makeup of the atmosphere and altering ecological balances at an accelerated pace. We can measure the physical toll of these shifts at the poles, where massive glacial sheets are steadily melting and collapsing into the warming waters. To track these changes in real time, researchers rely on a dense network of orbital satellites. These instruments download terabytes of telemetry every day, feeding global climate models that map the planet's fluctuating temperatures and rising sea levels. We are mapping our environment with immense precision, but the data reveals a harsh reality. Keeping all human existence restricted to a single, highly reactive planet is a significant mathematical risk. The first step towards securing our survival lies nearly 240,000 miles away, in a barren expanse of pulverized rock. Space agencies no longer treat the Moon as a trophy to be visited once and abandoned. It is an active, hostile laboratory. Planners are designing permanent scientific outposts specifically targeted for the lunar South Pole, where deep, shadowed craters may hold frozen water. Living there means enduring relentless solar radiation, temperatures that drop hundreds of degrees below zero, and abrasive silica dust that shreds mechanical joints. Engineers are countering these hazards by field testing pressurized habitats, advanced autonomous rovers, and specialized spacesuits designed for prolonged exposure. If human beings can establish a sustainable presence in the punishing lunar environment, we prove we can survive off-world. Every pressure seal tested and every life support error corrected on the Moon acts as a mandatory prerequisite for deep space travel. Maintaining these local missions require thousands of flight controllers, engineers, and scientists coordinating orbital mechanics from the ground. This diagram illustrates the enormous leap in scale we face. The distance between Earth and the Moon is relatively short, allowing for immediate communication and rapid emergency returns. As the flight path stretches toward Mars, a 3-day transit becomes a 7-month voyage. Radio signals take up to 20 minutes to travel one way, making real-time mission control impossible and rendering any catastrophic failure unrecoverable. The only way to mathematically reduce the immense danger of an interplanetary expedition is by mastering the complex logistics of lunar habitation first. Building this off-world infrastructure requires the combined financial and intellectual resources of multiple nations. Long before a launch sequence begins, ground-based observatories scan the sky to analyze orbital trajectories and identify exact coordinates for exploration.
The researchers calculating those flight paths today are building the exact architectural foundation that astronauts will rely on decades from now. When a launch vehicle finally clears the tower, it carries the accumulated work of generations of engineers. Expanding our presence beyond the Earth's atmosphere stands as our most significant shared endeavor. Breaking free from the gravitational pull of our homeworld means leaving behind the only biological safety net we have ever known. Coasting out into the deep vacuum of the solar system exposes the sheer, empty distance between the inner rocky planets and the outer gas giants. Zooming out further, our entire solar neighborhood shrinks down to a microscopic point of light within the swirling dust lanes of the Milky Way. We inhabit an incredibly small, fragile speck of rock, yet our capacity to build, calculate, and propel ourselves into the void has no defined limit. The immediate challenge is determining if the hardware and the humans tested in lunar orbit will be resilient enough to survive the brutal realities of the red planet.
When a new video exploring deep space or complex scientific theory is uploaded, it exists initially in a state of total isolation. Without external momentum, it remains trapped in a digital vacuum. This isolation is the primary barrier to distribution. Vital scientific knowledge can remain invisible simply because it lacks the initial energy required to move through the system. The platform's algorithmic gatekeeper evaluates content strictly through digital interaction signals. It does not prioritize educational value, it prioritizes engagement metrics. This rigid sorting mechanism creates a default state of exclusion. Even the most significant discoveries can be filtered out before they reach an audience. Bypassing this gatekeeper requires a specific type of input, direct interaction from the viewer. The video outro functions as a critical ignition sequence. It provides the instructions necessary to propel this knowledge past the algorithm and into public view. The like button serves as the first essential data point in this sequence. When a viewer engages, their node pulses, sending a signal that forces the algorithm's pathways to illuminate. This commands the system to distribute the content to a surrounding cluster of similar users. Subscribing and enabling notifications creates a permanent, high-speed link. This ensures that future uploads bypass the initial filtering matrix entirely, establishing a direct connection between the source and the viewer. The share directive utilizes a mechanism known as network bridging. By sharing a video, a viewer acts as a vector. They transmit educational content out of isolated algorithmic echo chambers and into entirely new user networks, such as friends and family. These combined actions transform a passive observation into an active distribution process, which allows educational channels to maintain their visibility in a crowded digital environment. The interaction sequence continues in the comments section, where the host asks viewers to identify their location. This request functions as a mapping mechanism. It identifies the geographic distribution of what would otherwise be an anonymous digital audience. When the host reads and responds to these comments, it creates a two-way flow of data. This interaction strengthens the overall structural integrity of the network. This process converts an anonymous view count into a specific identifiable point of origin. Commenting provides the final verification for the network, marking the precise locations where the information has successfully landed and turning a passive audience into a visible community. At a macroscopic scale, these cumulative interactions build a sprawling, connected ecosystem. Through these specific actions, the viewer becomes an active node in the American education tech community, providing the connections that keep these subjects visible. A few seconds of direct engagement determines which topics are prioritized in the broader digital landscape. This collective curation ensures that space, science, and technology remain prominent rather than being buried by less substantive digital noise. The final phrase, "See you in the next video," acknowledges the completion of this cycle, a signal that the network is established and ready for the next phase of discovery.